United States Department of Agriculture.
Good morning. My name is Penny Reynolds, and I am delighted to be able to speak to you today. I'm going to be talking about pilot studies and how, if properly done and properly conducted, they can be a very valuable tool for promoting the 3 R's in research. So what I'm going to cover in the next 30 minutes or so is what a pilot trial actually is, why it matters, how you can put a pilot study into practice, what kind, how large, and I will introduce the concept of what I call the feasibility trifecta. And then in the last bit of my talk, I will present a case study where myself and colleagues introduced non-aversive rodent handling to the institutional facility here at UF. So before I go further, I just want to mention my book, which came out last September on sample size for animal-based studies. I have 5 chapters all about pilot study and design, which is probably more than you'll ever need, but it's one of the very few places where it has all the information on pilot trials together in one place. So first of all, I'm going to talk about what a good pilot study is and why good pilots matter. So a pilot is just a preparatory mock-up or a rehearsal of a later definitive trial. It has to be small and it has to be nimble, because the job of a pilot study is to provide the evidence you need that the later experiment can work, does work, and will be worthwhile to conduct. That means, is the study possible to do with the resources you have? Is it sustainable? Will you be able to finish it off in the time with the people and the resources that you have? And is it suitable? Will it provide the sort of data you need to actually answer the research questions you would propose? So why it matters is that pilot studies are a major tool for giving your research the best chance that they will be successful. And a lot of people will refuse to face up to the fact that problems are a feature, not a bug of research, Murphy's laws. What a pilot study does is allow you to identify early on and fix problems as they may occur before you've invested a lot of time and money and resources, and especially animals, in a full-blown definitive study. So a good pilot study, above all, reduces research waste and reduces the waste of animals. So it matters because you can't analyze data you don't have. And in my experience, it's logistic issues, not the science, which sinks a large number of experiments that I've seen. Uncontrolled variation experiments because your people aren't trained, or they're learning on the job, or there's too much confusion in the protocols. If it's so variable, your experimental signal is just going to be swamped. In the worst case scenario, the entire experiment will be a bust, so you don't get any data at all. And as good a statistician as I am, I cannot work magic, and I cannot analyze data if there are none to be had. The second thing is that pilot studies enhance both the value and the quality of the results that you can obtain from your experiment by improving the rigor with which the experiments are conducted and by ensuring the validity of the results. So it matters because any study can produce data. But if the data are unreliable, untrustworthy, and just generally overall poor quality, they're worse than useless. First of all, for the direct harm they cause to the animals themselves, because the animals are wasted in experiments that are dumb. It causes indirect harm to human patients. Most of the research that's being done has the intent to be translational or somehow be applied to human and animal welfare. And patients can be injured or even killed by therapies which were projected on the basis of shoddy preclinical data. And there's plenty of examples of that. And finally, there's the harm that's caused to the wider scientific community because the evidence base has been distorted by irrelevant, unreliable results. It leads to people going down rabbit holes after false leads, wasting effort, time, money, animals. Examples of that are Alzheimer's and a lot of cancer research. And finally, pilot studies are encouraged by a lot of agencies, regulatory funding agencies, and some ethical oversight agencies as well. And this is especially true if experimental procedures are novel, if they're very complicated or difficult to implement, if they're is studies a sort of an exploratory study where you've got a large number of candidate agents or therapeutic interventions, and you have to select the best subset of those for testing. Pilots are especially encouraged if there's a conflict between what the experiment sees as the goals of their experiment versus the obvious animal welfare detriments. And finally, if a definitive study is requesting large, shall we say, absurdly large numbers of animals, they will be encouraged to do a pilot to see if it's even necessary to do that. Researchers also have the ethical obligation to publish their pilot studies, and there are now increasing numbers of venues which will allow this. And in order to publish using animals, you will certainly need ethical oversight approval. So, to be a good pilot study, a pilot study has to be planned and it has to be purposeful. So every pilot study, no matter how small, needs a clear statement of objectives. Why do you need to do it? Secondly, you need good methods and procedures documentation. What do you plan to do and how are you going to do it? Number 3, and this is where a lot of protocols that I read really get hung up. How will you know the pilot worked? What are your success metrics? Remember, a pilot study is supposed to inform the conduct of a later definitive trial. So what will be your decision criteria for proceeding with the full trial, for modifying the trial protocol, or for just aborting the whole experiment altogether? And finally, if the pilot trial works, what do you plan to do next? What's your follow-on action plan, and how will you use the information you obtained from the pilot to inform the later trial? What pilot studies are not? Again, this is the frequent feature of many protocols I've reviewed. Pilot studies are not just throwaway studies that you've concocted for the use of students who have no resources, they have no skills, and the research is not meaningful. Pilot studies are not fishing expeditions. We've had investigators requesting the use of 85,000 plus animals to find something. There's no purpose. They had no criteria to assess whether or not they were making any progress, and there's certainly no plans for follow-up action. So, of course, that's going to be denied. And finally, if you have a completed study and it couldn't find anything, you can't just relabel it and call it a pilot study. If it's underpowered, it was too small in the first place, and if there's nothing ever there to be found anyways, a null study, you can't just call it a pilot. It is what it is. Specific to veterinary clinical studies, many of them will request, say, 5 or 6 animals, usually companion animals, to assess safety, tolerance, or the efficacy of a certain novel compound or agent. They cannot do this. This is not the purpose of a pilot. They are simply too small. First of all, if the risk is known and it's so severe that it's bound to show up in a small sample of 10 or so animals, you shouldn't go ahead anyways. I mean, that's just unacceptable. Secondly, if you've got a small pilot study, adverse events are usually rare anyways. And so just because they don't show up doesn't mean that the compound is safe. So pilot studies are not the appropriate venue to assess safety and tolerance. Now I'm going to go into the details of how you make a pilot trial work, what kind of a pilot, and how large a pilot. This is what I call the feasibility trifecta, and I borrowed these terms from the community public health arena. They basically boil down into 3 items. Can it work? Does it work? Will it work? Can it work as operational, focusing on logistics? Are the data being collected properly? Does it work is the empirical. It focuses on the experimental endpoints. So these are pilots to assess if the data that's actually collected are meaningful. You can actually measure them. And finally, will it work is the translational phase. This assesses the validity of the study. Will the data be broadly applicable to a greater scope of patient pool, of different circumstances, and so on? So the first one, can it work? The priority is the logistics. Now, all experiments and observational studies as well really need to assess operational feasibility before they start. What's the work process? What tasks do you need to do? What order? What are you actually going to measure? Where are the bottlenecks in collecting data? How can you fix them? Are there any workarounds? How can you improve the process, make it more streamlined, less of a burden on your people? And the biggest thing, who's going to do the work and will they do it properly? This is not a statistical significance testing exercise. You do not need power calculations. In fact, they're absolutely meaningless. And you may not even need animals at all. So the whole point of this is that many experiments and even observational studies, even retrospective chart reviews, are complicated and there's a lot of moving parts. So the goal here is to make sure all your procedures are standardized and properly identified, that human error is minimized, and the performance variability, both within one of your people, because you don't want them learning on the job, you want them to be performing at a high level right from the get-go. But you also want to minimize the variability occurring between personnel. So the metrics are quite simple. Number of protocol deviations, you want to aim for 0%. Number of errors, 0%. Number of tasks completed, 100%, that kind of thing. Essential tools for these sorts of pilots are developing your task flow maps, your checklists, and quality control charts. Now, a task flow map is nothing more than a visual aid. It shows all your critical tasks in what order, and you can also use them to identify what happens when, who's going to do the work. And why I like them so much is that they are a quick visual aid to identifying critical bottlenecks or problems in your procedure. A lot of people have a tendency to fiddle around with the last thing that happens, where you can only really fix problems downstream by addressing problems upstream. So in this graphic of a surgical procedure in swine, number one place we had to start was habituation. If the animals are not sufficiently tame and handleable, nothing else to do downstream is really going to help. The second big bottleneck was securing the airway. So we had to insist that was correctly done and proper corrective actions were taken before you could proceed with the surgery. And the third one was the physiological assessment. Checklists are my favorite and go-to. It's just a quick list of all the tasks in task order and critical tasks that need to be done. So these are like the checklists that airplane pilots use. It doesn't tell you how to fly the plane. That's for the standard operating procedures. What the checklist does is a list that you read and then you do it and check it off. You do it and confirm that it was done. And finally, there's quality control charts. This is just to assure everyone that performance goals are being met. Now, these are not to be used as a tool for punishment. It's just to identify problems and see what improvements can be made. For example, in this graphic of critical errors made by an experienced and dedicated surgical team, we found that the number of errors went down just by writing sample times on a whiteboard because the number one problem was missing samples collection at the appropriate times or forgetting steps in the protocol. And the errors went down to 0 once we had a dedicated scribe who did nothing else but oversee all the procedures and make sure that they were done. So, for example, establishing operational and subject stability, human performance, here's our success metrics, predefined task errors, goals 0%, number of samples missed, goals 0%. Certain performance times, like securing the airway, should be 100% times within a 1-minute limit. And then the animals themselves, if they're subjected to surgery, they have to meet predefined target physiological values for oxygenation, ventilation, perfusion. So 4 simple metrics, easy to measure. If the animal is outside of these target zones, appropriate steps can be taken to fix that. So the next phase is experimental strength. Does it work? The empirical feasibility, and focusing on the key experimental endpoints. Again, there's no statistical significance testing or power calculations, but instead we rely on data plots, graphics, and data visualization tools. So you have to define which variables. They have to be relevant to the study. They have to be clearly defined, specific, and above all, measurable. So you can't just say you want to look at immune function. What specifically are you going to be measuring, like CD4 concentration? And then you quantify the best variables. For your experimental endpoints, they have to be large enough to be measured, stable enough to be reliable, and they shouldn't be really strange or out there. They should be at least in line with not only a research question, but also what available evidence there is in the research literature. Again, success is not determined by p-values after the data are collected. You are not hypothesis testing. So this is an example of an experiment where the goal was to determine coagulation dysfunction, but in and of itself, that has absolutely no meaning. So we had to define clinically relevant changes in a specific list of coagulation variables, and we had 30 candidate variables that had to be screened. We knew that some of the components, if there was a clinically relevant amount of dysfunction, it would comprise, say, 20% reduction in various components or functions, or duration of clotting times we expected them to be about 20% longer. And here it shows that even though there's a fair amount of variability, as you'd expect in a pilot study, they were still in the correct direction, meaning that we were on the right track for these particular variants. And finally, will it work? When the objective is translational feasibility, the priority is getting strength of evidence so that study results are true and unbiased. So this is methods-based, and in this phase, you need to incorporate all the aspects of a properly designed randomized controlled trial. You have appropriate comparator. There's random allocation of the interventions to the experimental units. There's allocation concealment, what's sometimes referred to as blinding. Inclusion, exclusion criteria for subjects and data must be predefined. The outcome measures, your experimental endpoints, must be clearly defined, specific, and measurable. And you need appropriate sample size estimates. So these are not only power calculations, but also operational calculations. How large a pilot? Again, all studies using animals do require a sample size justification, but this is not going to be power calculations for operational and empirical pilots. Your goal is information power, not statistical power. So you have to justify your sample size. And there's really two different kinds of ways of doing that, either no animals at all or just pragmatic concerns. So the zero model, this is a key pinnacle of placement. So you want to always consider alternatives before you obtain animals for purpose. Do the background literature. Are there any systematic literature reviews or meta-analyses? And for the neurological injury literature, Camerades is one of the best resources out there. You can also do targeted surveys of academic and industrial research organizations to get information that you might need. If the experiments are fairly complicated, then personnel will have to be trained, they will have to acquire specialized skills, and there will have to be standardization of techniques. And again, you don't necessarily need animals for that. You can use simulators, you can use carcasses, you can use culls, anything like that. And skill acquisition must be assessed on a regular basis to make sure that everybody is up to the same uniformly high standard. Pragmatic concerns are usually conducted before the study even begins. You need to do the math. How many subjects are available and how much money and time and personnel do you have to actually do the work? And sometimes this is nothing more than just basic grade school arithmetic, back of the envelope calculations. In more complicated cases, which I'll illustrate in a minute, you need to use a little more advanced sampling probability calculations. For example, one of the things that should always be asked for a pilot or a definitive trial is the study even realistic in the first place? Now, this is unfortunately a real protocol where a PI requested 500,000 mice for 3 years, but there were only 2 technicians listed on the protocol, and it was evident it would take at least half an hour to process each mouse. So what information do we need? Well, how many adequately trained people are there? How long does it take to do each task? How long will the study take? How much space is there? How much will it cost per procedure, per subject? What's the total study budget? Well, in this case, this very simple math showed that to process this many mice in 3 years would take about a century. So clearly 3 years is not the same as a century, and the study was completely unrealistic. The researcher really needed to rethink this request and, again, start thinking about appropriate pilots to find out what it was they actually wanted to do. Now, this was a far more interesting study. Some veterinary researchers wanted to develop a new screening method for the MYBPC3 gene in Maine Coon cats. Maine Coon cats, like many other insanely expensive companion animals, are very prone to a condition called hypertrophic cardiomyopathy, and the problem is current screening is fairly invasive. This was a new, far less invasive method, which promised to be significantly cheaper. So they wanted to know how many cats they needed for pilot study. Well, we had a register of about 320 cats in our catchment area, and the expected prevalence of this gene is about 30%. So we would expect that about 96 cats would be positive for this gene in our catchment area. Problem is how many samples for a pilot? Well, they thought that at least 5 positive cats would be needed compared to 5 negative cats, because the additional costs would be for establishing the presence or absence of cardiomyopathy with echocardiograms and other expensive things like that. So they could budget for at least 10 cats. So then the question becomes, we don't know who they are. So we need to know how many cats do we need to screen so that we can be sure of getting at least 5 cats with 95% probability. So this is a hypergeometric sampling problem. So before you begin to weep, you don't have to actually develop a macro for this. I already did that, but there are actually phone apps out there which will allow you to iterate through a whole set of candidate sample sizes and find the number which will meet these criteria. And in our case, we found the answer would be 28 cats would have to be randomly sampled from our registry of 320 cats to be 95% confident that we'd have at least 5 cats in that sample that were positive. So finally, in the last few minutes, I want to talk about a case study where we introduced non-aversive handling to our institutional mouse breeding facility. So this was a proof of concept test where our goal was strength of evidence, which would be determined by study validity, a randomized controlled trial, in other words. And the results of that are published here in PLOS One a few years ago. But before we did the study, we had to go through proper pilot testing to address stakeholder concerns, the materials, and our methods. So the stakeholders all want to know the same thing, is this new intervention going to be acceptable? Will it work? Will it can be successfully integrated into the workflow processes? But the different stakeholders are going to need different data. Veterinarians were the easiest to convince because there's plenty of literature out there. Senior leadership, we had to really wait until we could get cost estimates and find out how many people were complaining. Investigators were put off until later because what they are always concerned with is how it's going to affect their experimental results. We had to get the data first. So the priority was the animal care staff because the burden of implementing this fell most heavily on them in terms of time and the amount of work they're expected to do. So it was an iterative process. Train a few people joining the study, test drive, get feedback from them, reassess, change the protocol, add, drop, change, retrain, retest, reassess, and so on. So materials, we had to redesign the tunnels. We went from a round tunnel to a square tunnel, easier to store. When you drop them, they don't roll all over the floor. And it reduces the amount of furniture in the mouse cage because the pregnant dams would use them either as retreats, as latrines, or if their cage is accidentally flooded, they move their pups to the top. And we also had to make the tunnels shorter, not as long as they were. For the time on personnel, we just did a couple of simple, really easy trials, just try it out, time people out, see what the differences were between the institutional standard of tail lift with forceps. And we found that within 2 sessions, each person involved was able to reduce their tunnel cage changing times by at least half an hour per 100 cages. So once that was standardized, we could implement as the final stage, get our standard operating procedures, visuals all down, and then move on to the next stage. Does it work? Experimental endpoints. Well, this was easy because productivity metrics were already there in the facility records. So in this phase, we had to determine, is the data we actually needed present in the records? Sometimes that's a difficulty if the actual numbers you need aren't there. And then the second thing was, can we actually extract those data for research purposes? And that's required a bit of work. So that was the logistics of data entry and management in this phase. And finally, the proof of concept randomized controlled trial. We were able to assign two treatments, the non-aversive handling with tunnels versus the standard tail with forceps, and just followed naive monogamous pairs through their entire productivity cycle of 6 months. Count up the number of pups born, weaned, total litters, and so on. How large a study was a bit of a problem because we were limited by space and ethical constraints. We only had room for 100 pairs. We had 12 months of a hard deadline. And we couldn't just willy-nilly breed everything we wanted because pup production had to approximate researcher demand. Otherwise, the pups would just have been euthanized without being used. So we defined what a success looked like before the trial started in consensus with the other attending veterinarians. 5% increase in production would justify facility change in practice, 1 pup per pair. The problem was that this was not the same as statistical power. To get that level of statistical significance, we need well over 200 pairs over 2 years, which we couldn't do. Or 1 pup extra per litter, which was possible biologically, but unlikely. So it had to be made clear that operational significance was not going to be the same as statistical significance. And what we found was that, yes, non-aversive handling did meet the operational threshold for pups, just over 1 extra produced, not statistically significant. But the surprise to us was the litter attrition threshold, is that the non-aversive handling greatly exceeded the standard tail with forceps. In terms of number of litters weaned, the non-aversive handling, almost half of them did successfully, versus the tail lift with forceps, over half lost at least 1 litter.
USDA is an equal opportunity provider, employer, and lender.